Hello, this video covers the properties of chords in circles that has to do with distances for internal intersections and external intersections. What are the distances of chords? For my classes, this is 10.5 out of the textbook. So what you see here is a situation for proving the formula AC equals BD, which you can see on the top right there. Right? So this is your theorem up here at the top. So if you take the length of A times C, that should equal B times D. But why does that work, right? So this actually comes from similar triangles. And I'm going to go ahead and just go to this slide so you can see it. So if you were to put in those green lines and finish off two triangles, you could actually see that the two triangles are similar. How do we know? Well, we know that the vertical angles are the same here in the middle. And we also have that this particular chord, or sorry, that particular arc is being subtended by this angle here and also this angle here, which makes them equal to each other. And I could do the same thing going the other way and show that that arc is also being subtended by these top angles up here and up here. So you have angle-angle similarity, right? Angle-angle similarity for those two triangles. So I know all their side lengths are in proportion. So if I wanted, I could write a proportion, as you can see here. If I take A divided by D, that's kind of the short side divided by the longer side. That will be equal to the short side divided by the longer side of the other triangle. So I'm just writing a proportion here like we've done many times in the past with similar triangles. If you cross multiply, you'll get your theorem. AC equals BD. And that's really just the easy way to memorize it and work with it when you're solving problems. But just keep in mind that this comes from similar triangles, and the proof is from similar triangles, angle-angle similarity, and writing a proportion equation, just like we've done many, many times. So we're going to use that theorem eventually, but right now, sorry. So let's practice real quick when I look at something like this. Now keep in mind this point right here, that intersection point, is not the center. The center of the circle is somewhere else. So this works no matter where that intersection is. But don't think that things are bisected or things like that, like they might be if it was the center, because it's not. So what do you have to do? You have to just multiply those numbers accordingly and solve. So I'm just doing a little calculator work here just to make sure. Oh, that's just 5. Well, that was easy. Okay. Can you visualize the similar triangles? There's one there, there's one there. So you're just writing a proportion from two similar triangles. Same thing. They tell us that AC is 21, that's the whole distance. So this must be 21 minus x if the whole distance is 21. So I would have to multiply these out. Uh-oh, looks like we're getting a quadratic. And, whoops. Let's move everything over to one side. Everything's on the same side. Does this factor? Looks like 16 and 5 would work. Right? I multiply those together, I'll get positive 80. When I add them together, I get negative 21. Solutions would be 16 and 5. Which one's 16 and which one's 5? Well, the way they look, this one would be 5 and this one would be 16. But technically speaking, it could be the other way as well. Doesn't really matter. Okay, we got a new theorem here we're going to look at. But first, to kind of warm up to it, you can see we have an external angle there. But to warm up to it, we're just going to work with some numbers to see how things work. And then we'll summarize it in a proof. So CDE is 60 degrees. BCD is 95. So those are given to us. And I just want to work my way through the rest of this triangle. Now, if you ignore the part on the outside and just look at the quadrilateral inside, I would know that this angle is 120 because they're opposite angles on an inscribed quadrilateral. Same thing with the 95. This is going to be 85 degrees because those are opposite angles on an inscribed quadrilateral. Now, if you just use a straight line, right, that's a straight line, then I know this angle would have to be 60 degrees, and I know that this one has to be 95. Oh, do you see how those are the same as the ones we have over here? Oh, okay. And then also in a triangle, I can make a triangle here, right, which they already have kind of made for us. If I look at that triangle, 95 and 60, so that's 155, so that's got to be 25 degrees in the little corner there. Okay, so you could fill in all these numbers, EBC, BED, ABE, AED, and BAE, 25 degrees. Okay, so where's that taking us? Well, we're going to end up with similar triangles. And maybe you can see it here right now. Let me get some different colors. I have that little green triangle I just made, but I also have this larger red triangle here. So those are your two triangles that are similar to each other. How do we know? Well, this angle down here is reflexive. That's reflexive. You can see the 60-degree angle there is the same as the 60-degree angle here. And then I also have the 95-degree angle there and the 95-degree angle here. So we have angle-angle similarity. No matter what the numbers are to start off with, it'll always work out that way. Those will be the same. So those are similar triangles. If they're similar, then I can talk about their side lengths using proportions. So let's look at it in a little more general. Again, here's one large triangle. Here's one smaller triangle, right? And we said that this angle had to be the same as this, and this one had to be the same as this, and this was the same as itself with reflexive. Now you'll notice that they are similar, but the smaller one is kind of flipped over from the larger one. See where the double angle is compared to this double angle? Those are kind of flipped over from each other. So when we write a proportion, we need to keep that in mind. So let me go from small triangle to big triangle. So C on the small triangle is the same one. Like if I flip that green triangle over, it'll be the same as A plus B, or I should say it corresponds to the A plus B side of the red triangle. Then let me do A on the small triangle. And if you flip it over, it'll correspond to C plus D on the large triangle. So this is the proportion that I have. You can see it's small triangle to big triangle equals small triangle to big triangle. And just making sure that the corresponding sides are in the right spot. So when you cross multiply this, you're going to get what you see up here, what we were trying to prove. So you just cross multiply and that's your theorem. So to kind of put it in terms for you, maybe the easier way to remember it is I'm going to take the outside length times the whole length across, which is what I see here. A times A plus B. And then I'll take this side, the exterior part, times the whole length. So it's exterior part times the whole length equals exterior part times the whole length. You can think of the similar triangles, but to be honest, to run through the similar triangles every single time is difficult, and you can get confused easily, I think. It's easier just to kind of go with the theorem and know the quick way to use it. But keep in mind that it does come from similar triangles. This should be a proof that you're able to do. Right, there's another slide in the notes kind of with the same stuff I just did. Okay, so let's put it to use. What do I do? Well, the easy way is the exterior times the whole length, 6 plus b. And that should equal the exterior times the whole length. This is where students make mistakes often. They just use 10 instead of using 18, or they just use 8 instead of 18. Make sure it's the whole length. And then it's just a matter of solving. I'm just going to go ahead and do this on the calculator and get a number. So I'm taking 8 times 18 on the right, and I'm going to divide that by the 6, and then I'm going to take away the 6, and I'll get 18. Should make sense. You could always plug the numbers back in and make sure that works. Like on the right, we had 8 times 18, which is 144. On the left, we have 6 times 24, which is 144. So it works. Right? It looks a little weird just looking at it like this, like why does that work? But just always keep in mind it comes from those similar triangles that we have. That's where that comes from. Okay, another one very similar, but let's run through the numbers. Arc WN is 80. NP is 140. And we're looking for angle P to begin with. Well, P is half of the 80 because it's an inscribed angle. NWM. NWM is this angle here. That's also going to be 40. Why? Because it's subtending this arc. This is one of those exterior tangents, right? Subtending the arc. So it's still the inscribed angle rule where it's half of the arc. PWN, PWN, that's over here. This is subtending the 140, so it would be 70. PNW is the other one. We can subtract that from an 180. So 110, that would be 70 as well. Okay. WNM, so that would be 110, right? We can see that that's going to complete the straight line here, so that would have to be 110. Okay, so this is 40, and then we have, I'm going to do this, get this exterior angle here, so that's 150, this would be 30. And what we're supposed to see here, which is a little difficult to see maybe, is that we have two similar triangles again. We have a smaller triangle here, which is a 30, 40, and 110 degrees. And then we have a larger triangle here, which is also a 30, 40, and 110. If you look closely, this large angle is 110. It's the 70 plus the 40 up there. So the smaller red triangle and the large green triangle are similar triangles. Keep that in mind. Here's a proof of what we just kind of did. I'm going to connect the pieces here. We said this angle, well, sorry, this angle is reflexive. Use some different colors here. The angle I made a double arc right here would be the same as this one. This angle is the same as this one. All right, take that back. This whole angle, sorry, is the same as this one. So you have your similar triangles. Let me put some color on there so we can keep it straight. All right, so we have small red one and large green one. I don't know if that helps or not. But... So if we want to prove a rule on this, it's just what we did before, writing a proportion with similar triangles. So let me take A, on the red triangle, right? A on the red triangle. If you flip that over, it'll correspond to C on the green triangle. You have to, in order to get the triangles to match up, you'd have to flip one of them over. So on the small triangle, I have C on the top here. And if I flip that over, it'll correspond to A plus B on the green triangle. So it's just writing a proportion. And if you do cross multiplying, well, it's already written for us. You'll get this, right? If you cross multiply what we were trying to prove. So let's take this is kind of a nicer written out version, I guess, maybe a little. But it's just similar triangles and writing proportions. Let's put it to work. So what do you do to follow the rule? Well, it said you take this 10 times its whole length, but in this case, the whole length is just 10. Like, it doesn't go across the circle. There's not another piece to add on. So it really is just 10 times 10. The other part, 4 times the whole length. So you got to have 4 plus b in order to get the whole length. Then it's just a matter of solving. So you should get b is 20. Whoops. No, that was right. b is 21. Okay. Like I said before, you can go through the whole similar triangle situation, but it's just time consuming and tedious, and you can make mistakes. It's easier just to follow the rules as long as you know where they come from. Here's another example. I guess I'll write up here. 18 times 18. The outside times the whole length equals outside times the whole length. Oh, I can see this is a quadratic again. So we get 324 equals x squared plus 24x. We solve for 0. And you get that. We might be able to do factoring. I'm going to try and see what I get for solutions for this. It doesn't come out even, it doesn't factor. So you have to use quadratic formula. X equals negative b plus or minus square root of b squared minus 4ac all over 2a. All right, I'm going to try to put that down here. So a is 1, b is 24, and c is the negative 324. That's not easy. Negative 24 plus or minus square root 24 squared minus 4 times 1 times the negative 324. Solve that all out. 2 times 1. Okay, if you just solve that out, you will get negative 2? Yes, negative 12. No, yeah, negative 12 plus and minus the square root. Actually, it's plus or minus 6 root 13. And that's the best you can do. Of course, you can get it as a decimal, that's fine, but this is just getting you to practice quadratic formula. I wouldn't worry about the quadratics so much. Concentrate on just writing the equation properly first. But this is one of those times that we try to get you to practice algebra skills just so you are ready for Algebra 2 next year. Okay, a little more practice. Well, this is an interior one, so we're going to go W times 16 equals 12 times 35. And when you try to solve that, you get 105 over 4, which of course you can change to a mixed fraction or a decimal. This is a little bit of a challenge problem. I'm going to just stop right there. You can give this a try. Let me know if you got a question about this. We can work this out together or put it on a separate video maybe. It's not worth the notes. It's just kind of an extra challenge problem.